All right. First of all, I'd like to thank the organizers for inviting me to give a talk. I saw that Liam McAllister gave a very nice talk in this workshop asking for help, but he didn't actually tell you exactly what kinds of computations that he wants you to do. So I'm going to talk about that. So in reality, what I really want to talk about is not this grandiose title, but really some theoretical challenges I face in string pheno that I really want you to work on. Okay, that's my talk. So the plan of the talk, henceforth, will be the following. First, I'll introduce some difficult problems in string phenomenology that we're facing, with the hope that some of you will find those problems interesting. Somehow, this is not the full size. Some part of it is cut out. Let's use this then. It's as good as the full screen. And so this talk will be mostly two parts. In the first part, I'll give you a quick overview of difficult problems in string phenomenology. And in the second half, I'll describe some partial progress I made, and then I'll talk about which directions I think are promising. Okay? So what do we want to do in string pheno? What we really want to do is to connect string theory to the real world. This is a big goal, and there is a long way to go. At least the least thing that we need to do is to first find a solution or confirm the existence of a solution in string theory that has the following features. First, 4 dimensions must be non-compact. We need some realistic particle physics, and SUSY must be broken at low energy. I don't mean TV scale SUSY breaking, but compared to the Planck scale. And the cosmological constant, it'd be better if it's small and positive, or if you don't like this, you can also try to find quintessence. Of all those things, I think we have a rather good understanding of how to engineer a particle physics sector in string theory. Really, the problem is to find cosmological solutions like dizita or quintessence, whose theoretical control is demonstrable. If you want to just find a crappy dizita, I think you can possibly do it, but really, the problem here is that we want to make sure that control's really good so that we can really trust the solution. Okay, so to really talk about concrete problems, I need to first set up the stage. So I'll follow the most beaten path. But by that, what I mean is that I'm going to choose type 2B string theory, and then I'll compactify 6 directions on Calabi or nth fold. It doesn't mean that this is the best way forward, but it is something that I know and love, so I'm going to just do it. And then we'll turn on some round fluxes and SNS fluxes to free some moduli, and then we'll think about breaking some SUSY at low energy. And then the goal is to find some isolated vacuum by combining those ingredients and compute their physical properties and make sure that we have good vacuum. And as I said, this is probably not the best way. And as was illustrated in this recent paper by Bruno, Eva, and Gonzalo, we might not really need to break SUSY at such a low energy scale. Even if you break SUSY at KK scale, for example, they were able to convincingly argue that you might be able to retain some computational control. So probably what we also have to do is to explore some other options, not just type 2B, but I'll stick to type 2B for today. Okay, so then how do we find interesting string vacuum? I'll use the language of 4D n=1 effective field theory. And in this EFT, there are holomorphic moduli fields, and they will determine the vacuum structure. Especially there are the 3 quantities that are very important. The first one is the Kavli potential, which is a real function of moduli. And this is the superpotential, which is a holomorphic function of moduli. And this is the explicit SUSY breaking source, which is obviously a real function of moduli. And then what you're supposed to do is to compute this effective potential by combining those ingredients. Then, rule of the game is to drive this effective potential as precisely as possible, and then you just need to minimize it. Doesn't look awfully difficult, but somehow this is very difficult. Why is it? There are 2 good reasons. One reason is that search space that you need to scan through is just too humongous. And there are infinitely many choices you can make, practically infinitely many Calabi-Yaos, infinitely many fluxes. And it is really difficult to know a priori which is going to be an interesting choice. And I think Liam talked about how to overcome this challenge. What I'm really going to talk about is that it is really difficult to even put an error bar on the effective potential, which means that we really don't have a good understanding of the computational control beyond the leading order. This is the thing that we're really suffering from, okay? And then this happens not only in type 2B, it also happens in M-theory on a G2 or heterotic on a Calabi-Yau. Any kinds of compactifications will suffer from the same problem. Okay, so we need to talk about why is it so difficult to compute the effective potential. Slogan of today's talk will be the following. We're not so bad at computing holomorphic data, but unfortunately we're really bad at computing non-holomorphic data. And this will come up again. So let's start with the superpotential, which is nice because it's holomorphic. In type 2B string theory, the superpotential can be written in terms of the tree-level contribution and the non-perturbative contribution. The reason why I'm not including any like string loop corrections here is because there is this nice non-renormalization theorem. And for example, if you want to compute the tree-level superpotential, which is given by the fluxes, you just need to use some simple algebraic geometry to compute it. Easy peasy, not that horrendous. The problem is really the non-perturbative superpotential. What Witten taught us in '96 is that, okay, if you're imagining a D-brane wrapped on some cycle, checking whether or not the non-perturbative superpotential is generated by such a D-brane is a topology problem. So it is doable. But suppose that you want to know some fine physics. Say that you want to understand some axion physics, and then you really want to understand how this prefactor depends on moduli. This has been really difficult, despite the fact that this is a holomorphic function of moduli. Why is that? Let's look at some explicit formula to evaluate the non-perturbative superpotential. Quite unfortunately, despite the fact that the result must be holomorphic, the intermediate step that you need to take to compute this non-perturbative superpotential involves the Keller potential and the spectrum, open string spectrum, ending on D-branes, both of which are not holomorphic. So despite the fact that this is holomorphic, it is actually very difficult to compute because we do not know the open string spectrum. For example, this is the partition function of open strings ending on the D instanton. And this is something that we do not really know how to compute. But of course, this is a holomorphic quantity. You might guess, okay, there must be a better way. Actually, there is a better way. So recently I proved that actually this whole combination can be rewritten in terms of topological string partition function at one node. So you might be able to just compute it if you have a good understanding of the topological string partition function. So it was difficult. It is somewhat still difficult, but anyhow, not so horrendously difficult. Now, really the problem is to compute the topological string theory or compute the so-called Newsuz index, which will show up again. Now, let's talk about the real difficult problem. Why is it difficult to compute the Keller potential? It's because the Keller potential is not a holomorphic function of moduli. In the context of orientable compactification, we still have some nice structures. That structure is the following. The Keller potential can be written in terms of the N2 contributions, which is basically coming from the Calabi-Yau. And then there are some contributions that are coming from N2 to N1 breaking effects, such as fluxes, D-branes, O-planes. A nice thing is that the tree-level contribution in the absence of the flux is essentially computed by the prepotential. To really relate the prepotential to the Keller potential, you need to do some work, but essentially it's determined by the holomorphic function. And then what you can do is to use S-duality, mirror symmetry, and many other dualities to bootstrap this N2 part of the Keller potential really precisely. So this part we know very well, because the seed is the holomorphic function. On the other hand, quite unfortunately, it appears that there is no trick that you can really use to compute this guy. So probably the only way you can compute it is by doing direct computation. So say that you want to do a direct computation. What are you supposed to do? If you insist on doing well-defined computations, then this is the computation that you're supposed to do. You need to draw some worldsheet diagrams, and then you need to insert 4 moduli, say 2 holomorphic moduli and 2 anti-holomorphic moduli. And then you can evaluate this diagram at a particular point in the moduli space. And if you take the low energy limit or soft limit, then this is the expression that you get. And using this, you can compute the curvature of the moduli space, and then from that you can read off the Keller potential. But the unfortunate thing is that we do not know the conformal blocks, especially 4-point conformal blocks of the Calabi-Yau CFT, and we do not know the spectrum. So this is a fantasy. We cannot do that. There are some tricks you can use to simplify the problem, which was developed by Joe Minahan, for example. The idea is as follows. What you do is to relax the momentum conservation, or you can go to off-shell by a slight amount. And then the idea is to just compute the 2-point function to directly read out the kinetic action of some moduli fields or gravitons. It's very much like the wave function renormalization computation in the QFT that we do. This is somewhat simpler than before because now you just need to know 2-point conformal blocks, but still it is very hard because you need to know the spectrum, which we do not know how to compute in general. And let me also mention that this is the trick that was used by most of the papers that attempted to compute the one-loop correction. Okay? Yeah.
Sorry, well, what's the big deal about the conformal block? I mean, there are recursion relations.
Yes, there is a recursion relation, but we do not even know the tree-level conformal blocks for the general Calabi-Yaus, right?
You just mean it's supervisorial algebra? I mean,
we do not know the vertex operators and then their fusion coefficients.
Okay, but that's not part of the conformal block.
Yeah. Oh, yeah. I was talking about I meant conformal block in a very loose sense. Yeah. Okay. Now let's talk about supersymmetry breaking effects. This is also very difficult to compute. It's not the case that we know nothing about it. We know something about it. For example, if you use an anti-D-brane to break SUSY, a string scale, let's say, then we know the SUSY breaking effects up to the leading term in alpha prime and G string expansion, for example, which is basically the dBi action plus the Chern-Simons action. The problem is we like to break SUSY at low energy. To do that, what you're typically supposed to do is to put an anti-D-brane where there is a huge IR redshifting. And to cause it, what you typically do is to put a lot of fluxes in a very small region. And then that will cause the tip to have a very small size, typically. Which means that this leading order alpha prime and G string expansion may not be the best thing to do. Of course, in reality, what you can do is to tune some fluxes, like Raman-Raman flux F and NSNS flux H, to reduce the curvature at the tip somewhat. But you cannot do that in an arbitrarily way that you would like, because there is some bound on the tap hole, there is the bound on how much tuning you can typically do. So typically what you'll end up finding is that alpha prime corrections to the D-brane tension in explicit compact Calabi-Yaus can be quite sizable. And we need to really compute them. And then so far, I don't think the complete answer of the alpha prime corrected D-brane action is really known. So these are the problems. Let me summarize the challenge here. The challenge is really that we do not know enough about the worldsheet CFT in a Calabi-Yau interval background. More precisely, we do not really know how to compute string amplitudes in Raman-Raman backgrounds to really go beyond the leading order in G string, for example. We do not know the string spectrum. We do not know the D-branes and O-planes, really, except for their zero-mode approximation. And for example, we do not know the OPEs of the vertex operators. And all of these are making us really suffer. So despite all the challenges, I still believe that we might be able to make some progress. So I want to talk about them. And I think there are largely 3 threads to follow. This is a very important thing. We need to better understand Calabi-Yau CFTs overall. Unfortunately, I have nothing to add about this, so I'm not going to talk about that. The other thing is the following. So although like some quantities that we like to understand, for example, the Keller potential, they are not protected in the low energy FT, but somehow if you can relate them to some protected quantities of some other problems, for example, the worldsheet CFT, then you can probably make more progress. So that's something that I want to talk about in a very quick manner. And then The other very important thing is that we need to learn how to compute string amplitudes in the Raman backgrounds. So I'll spend more time on it. And do you have any questions so far?
How weak have people been able to make the curvature at the tip? You said basically that's the limiting factor here, leading you to want to do these stringy corrections.
Yeah.
And people have done these searches using computational methods. Yeah, so just what's the status of that? How weak can the curvature be?
Yes, so I'm not directly involved in that search. I think Liam and his collaborators are doing the search, but my understanding is that if you just want to reduce the curvature, you can do a very good job. But if you want to reduce the curvature and at the same time do some alignment so that the SUSY breaking scale is somewhat comparable to the ADS scale, then it becomes a double fine-tuning and it becomes really difficult. So I think that's basically the gist of the problem. We want to do many fine-tunings at the same time, and it's difficult to find a good one.
Sorry, one more question. People have been working on like numerical approximations to the Calabi-Yau metric.
Yes.
Is that of interest here, or is that, when you say better understand Calabi-Yau CFTs, is that something you need, or is it?
Oh yeah, I think that would be a great way to make progress. For example, we have some understanding that the loop corrections to the effective action from open strings, for example, will be dominated by the low-lying open string states. And then that can be computed, the mass of them can be computed if you know the geodesic length between some D-branes. And that can be also computed if you have Calabi-Yau metric. So I think that is something that we should really study and push further. But I have almost nothing to add at this point. Great. So I'm not going to really talk about it in detail, but here is one thing that I want to emphasize. Calabi-Yau compactifications are special. They are nothing like generic 4D n equals 1 low energy FT. What I mean by that is the following. If you want to compute the string loop corrections to the Keller potential, really what you're supposed to do is to compute loop corrections to the graviton kinetic term and the moduli kinetic term in the string frame, because the string amplitude computation will give you the answer in string frame typically. And then you can use them to read out the Keller potential. As we know, and as I've been emphasizing, in low energy FT, the Einstein-Hilbert action or the kinetic term for the graviton, or for example, the kinetic term for the dilaton, are not protected quantities. So there is no way that you can guess that, okay, this must be computed by some indices. The surprise that I found recently, although I'm not going to talk about the details of the computation, but you can ask me later, is that in string compactifications, the string one-loop correction to the, for example, Einstein-Hilbert action and the dilaton kinetic term are actually computed by the protected quantities. And by the protected quantities, I mean the Witten index of the worldsheet CFT and the new supersymmetric index of the worldsheet CFT. And the new supersymmetric index is not really an index. It is an index in the sense that this quantity is not sensitive to the D-term deformation of the underlying theory, but still it is a protected quantity, so you have some hope of computing it in explicit Calabi-Yaus. Such that, for example, if you compute an annulus contribution to Einstein-Hilbert action, this is the formula that you get. So it is really computed by those protected quantities. So what I want to emphasize is that orientable compactifications are not generic 4D n equals 1 low energy FT. So there could be some mileage we can get out of that. Okay, and this is not only the case in the type 2, this also happens in heterotic string compactification. So it seems to be quite a universal phenomenon. Then let's talk about how to compute string amplitudes in the Raman backgrounds. Is there any question? Okay. So why do I care about Raman backgrounds? Because in any attempt to find a realistic cosmological solution in string theory, you'll have to invoke non-trivial Raman fluxes. So really, there is no way of avoiding doing computation with Raman fluxes, and we need to learn how to compute scattering amplitudes in such backgrounds. Of course, we all know that doing RNS superstrings in Raman backgrounds is very difficult. But it is not the end, because there are some formalisms that you can use to study those backgrounds. I'll choose string field theory. The reason why I want to choose string field theory is because I learned in the past few years from Xi and Ashok that string field theory is very systematic, very usable, easy to use. I really want to put an emphasis on that, to study generic string backgrounds, as long as you have chosen your problem carefully. Okay? So in that regard, and using string field theory, Minjae and I found a perturbative background solution of string field theory that corresponds to a particular flux compactification of Giddings-Kachur-Polchinski, which I'll write it as GKP. And then I'll describe how you can find such a background. And with this background solution, now we can start doing computations in GKP or in more general string flux compactification. So the rough plan is that I'll first review GKP, and then I'll then tell you, so what is this string field theory and how you can do computations with string field theory, okay? So what does GKP aim to do? GKP wants to stabilize some moduli, notably complex structure moduli that basically determines the shape of the clavier and the exoductant with quantized Raman and NS fluxes. This quantized will be very important. So let's study type 2B on an 0307 rentable of a clavier by following the lead of GKP. What you're supposed to do is to turn on those Raman 3-form flux, which is now written as F3, and you need to turn on NS flux, H3, and then you just do the dimensional reduction. And this is the effective potential that you get. The detail is not really important. What is important is that the effective potential will vanish if this particular linear combination G minus vanishes. And this particular linear combination is a complexified 3-form flux. And this vanishes when the complexified form is 2,1 plus 0,3, which just tells you that, okay, you need to fix the complex structure moduli to minimize the potential. And at the minimum, you have this relation. And simply what I want to do is to reproduce this using string field theory so that I can set the stage for further computations. And as I told you, I'm going to use string field theory. So what is string field theory? In a very simplified form, string field theory is a map from a well-defined worldsheet CFT to some off-shell data. For example, off-shell action or patent goal for string fields. String fields here will be denoted by psi, which basically describes the local fluctuation around the worldsheet CFT background. For example, in bosonic string theory, you can just collect all the vertex operators, reasonable vertex operators that you know, and then combine them into one single thing and then call that the string field. The important thing in string field theory is that you don't have to impose the on-shell condition. So for example, p squared for this guy doesn't have to be 0. And then what you can do is to use this off-shell string field to compute off-shell amplitudes. And from the off-shell amplitude, you can read out the effective, the string field action, which means that you also know the Feynman diagrams or Feynman rules for a string field. Then what you can do when you have the action is that you can just use the Feynman diagrams and Feynman rules to study stringy amplitudes in a new background that you cannot really study using RNS, for example. And that's why string field theory is really great, because now you can use this off-shell action to study Raman backgrounds, for example. But it took some time for us to be able to really use string field theory for like GKP, because the string field theories for all superstring theories were only recently constructed following the work of Sen. And after this construction of string field theories, there have been many papers that are applying string field theories to do many difficult computations that you cannot really do using RNS. So I really think this is the right time to start learning and doing string field theory. It's quite exciting, to be quite frank. So why string field theory? Although I've been telling you string field theory is great and all, why in particular for me? So in this recent paper by Minjae and Scott and Xi, they actually pioneered how you can use string field theory to study Raman backgrounds. The idea is really simple. What you're supposed to do is to start with the worldsheet CFT that describes the NS background, and then you can deform it by turning on some Raman fluxes. For example, if you want to study PP wave background in type 2B, what you can do is to start with this simple, nice background, which admits the worldsheet CFT description, and then you just turn on this vertex operator for the Raman-Roman flux. And then in the worldsheet CFT, we're not really sensitive to the quantization of the Raman-Roman flux, so you can just treat this mu as some small perturbation. And then they solve the equations of motion in string field theory perturbatively in mu to find the PP wave background to do many computations. The reason why I want to stress perturbatively is because string field theory action involves infinitely many terms for infinitely many fields. So if you just want to do some like random deformation, you'll have to do a very painful computation. So to avoid that happening, it is really important to set up the problem such that you can do some perturbation theory, okay? And then in the same paper, they also studied ADS3, which was really impressive in my opinion. Anyhow, now let's get back to GKP. I want to use string field theory that corresponds to study flux compactification. As an input, as I told you, we need worldsheet CFT. The closest worldsheet CFT that you can find is the worldsheet CFT. So I want to keep things simple, so I'm going to talk about toroidal compactification, but if you're more ambitious, you can think about Calabi-Yau CFT, but let's make things simplified and think about toroidal compactification. So I want to construct some worldsheet CFT from sphere to the target space, from RP2 to target space, and disk to some D-branes. Crucially, what I'm going to do is an illegal thing that I'm going to set up the computations, I'm going to set up the system such that the topology cancellation is not satisfied. This is a bad thing to do in the usual string perturbation theory, but this is a perfectly fine thing to do in string field theory. The topology cancellation condition will come out as one of the equations of motion. So if you cannot solve the equations of motion, then your topology cancellation is not solved, but if you can solve it, then that's great. Your solution is consistent. And as I told you, string field theory action will involve infinitely many terms. So what I really want to do is to make sure that when I turn on the Raman-Roman fluxes and NS-NS fluxes, I can treat them perturbatively. But the puzzle is the following: these are quantized fluxes. H and F are not small numbers. Of course, you can say that, well, in the case of Raman-Roman fluxes, we have this G-string factor. So probably when you have a small G-string, you can treat this part perturbatively. But what about this? Yeah? If you cannot really treat them as a small perturbation, then we cannot describe GKP using string field theory. But it's not the end. The resolution lies in a simple observation. What we know is that the OPs of the worldsheet fields depend on the target space metric, and the target space metric depends on moduli. In particular, what this means is that these vertex operators have additional dependence on moduli, for example, complex structure moduli and Keller moduli. And what I can do is to choose my favorite way of choosing fluxes. For example, in my paper with Min-jae, we chose the fluxes following this paper. And what happens if you make the flux choice prescribed in this paper is that the NS-NS vertex operators scales like z to the minus 1/2. And Raman-Roman vertex operator scales like G-string times z to the 1/2. Then, basically, you can do a double scaling expansion. You can go to a regime where G-string is small, complex structure is large, where the ratio is fixed. And then you can treat the quantized fluxes as small perturbation. Okay? In our paper, we call this the epsilon expansion, but really what I really want to emphasize is that yes, we can solve the background solution perturbatively. And if you write the equations of motion now, it looks really simple. So this is the first order equations of motion. This is the second order equations of motion. Basically what it means is that the flux that you turn on is supposed to be marginal. Easy. It is understandable. Now let's talk about the second order equations of motion. So despite the fact that we have reduced the number of terms that we need to consider, there are still infinitely many string fields. But for the massive part, you can solve them really easily because the BRST operator is invertible. So this part comes as free. The difficult part is the massless part. To do that, you need to do some work, but you can find a solution. A very satisfying thing for me was that the necessary condition for the existence of the string field theory solution was that the effective potential of the low energy supergravity is minimized. It could have been much nicer if this was the sufficient condition, but it was a necessary condition, but anyhow. And now with this background solution, we can now compute string amplitudes in GKP backgrounds. This is something that we're currently doing now. Okay, let me conclude. Our ability to study string phenom is severely limited by our lack of knowledge of string theory. There are two main challenges. One thing is that we do not know enough about Calabi-Yau CFT. The other one is that we do not know enough about how to study Raman-Round backgrounds. I told you some partial progress I made. One thing is that oftentimes in string compactification, some unprotected quantities in the low energy FT might be related to protected quantities of some different problems. If that happens, that's great. And then string field theory allows a systematic and easy to use method to study Raman-Round backgrounds. Now, in my opinion, it seems more reasonable to make some computational progress along this line. So let me finally talk about some interesting problems that I want some of you would like to solve. So I think it'd be really interesting to really understand why this hidden protected quantity is appearing by doing some on-shell computations. And then also it'd be interesting to study more moduli terms like Kähler moduli and complex structure moduli. And what happens over and over and over again is that this new supersymmetric index shows up as a result of the computation. So it might be also really interesting to understand how to compute this in a Calabi-Yau compactification. And Minjae and I are computing some string tree level and loop amplitudes in GKP backgrounds and in the quintic. And I think it'd be very nice to build tools to compute anti-D-brane tension in the flux background to better understand SUSY breaking. And of course, we need to better understand moduli stabilization in other corners of string theory. Right, I'm done.
Questions?
I was wondering, in your string field solution at second order, did you check that it's supersymmetric?
That is something that we have not checked. We are expecting that the solution is supersymmetric, but we're still checking.
Is the background H flux supposed to be uniform, constant?
Yes, H is uniform and constant.
I see. One concern I have is because the way the string field solution is written is not manifestly, let's say, doesn't have the H flux enters through the B field doesn't have this shift symmetry.
Yes, exactly.
And in my recent experience, sometimes it's not obvious to recognize whether you have turned on the non-trivial dilettante profile or not.
Mm-hmm. Yes, yes.
So, but in principle, checking the SUSY will make sure that you have the right solution. Otherwise, there might be a family extra solution that you don't want.
Yeah. I completely agree with you. That's why we're checking whether or not we can solve the equations of motion in RNS sector. The reason why I'm more confident is that you can write down the low energy FT, and then the low energy FT solution has SUSY if the superpotential is exactly vanishing. And then in this example that we studied, superpotential is also exactly vanishing. So we are expecting that the SUSY is preserved, but the computation is to be done.
I would just suggest a possibility that there might be, you might end up finding more solutions than you want. But
wouldn't that be a good thing, though? Or maybe?
Yeah. But
yeah, to be seen.
Any other question?
So very nice talk. I have a question. So you treat the Raman flux perturbatively, right?
Yes.
So how far can you go, and where do you see the quantization from string field theory?
Yes. So how far I can go, I'm not really sure. That is something that we should try to understand where this method will break down. Whether or not we can see the quantization. Yeah, this is a very interesting point. So we know how to see the quantization of the NS-NS flux from string field theory. We know how to see the quantization of, say, the D-brane tension or D-brane charge. If you combine them and then if you require that, okay, whatever Raman-Roman flux that you turn on, the consistent solution should have a solution to the equations of motion, then that basically fixes the Raman-Roman quantization condition. So that is something that is kind of expected, because if you turn on quantized NS flux and then if you have a sink given by O-plane that can be only quantized, then the Raman-Roman flux as a constraint should be also quantized. So it's not something that is very special, but yeah, I'm not sure if there is a different way to see the quantization of the Raman-Roman flux at this point, though.
Thank you.
Thanks for the nice talk. Is it possible to include, say, a probe D-brane or something like this in the string field theory calculation?
Yes.
As, say, a toy model for, say, visible sector or standard model?
You mean the 7-brane, which is not an SOH stack? I think SOH stack is something that you can deal with string field theory or string perturbation theory, but I'm not sure how I can study, for example, like some D7-brane that is not really on top of O7 planes, because string coupling will blow up or it will stay order 1 somewhere. And yeah. D3-branes are fine, because D3-branes, like, they don't really source the dilaton. So D3-branes are okay, but D7-branes are challenging, for sure. We need something else than just usual string perturbation theory.
Any other question? Well, if not, let's thank the speakers.